Good evening, everyone. My name is Joanna Wu, and I am live streaming from Trottier Observatory at SFU. So you should be able to see on your screen there on the left if you. Hi, everyone. Sorry about that. Having some technical difficulties. Okay. I'm having some technical difficulties, so I turned off some of the little features of this live stream. I apologize for that. But hey, I'm back. Here we are with Jupiter. I think yes, things are much more responsive now. Not sure why this worked last time and it's not working today. So hopefully you can see what's going on. Okay, so let's talk about Jupiter. So I really apologize for that, but we are still looking at Jupiter right now, and we are looking at the shadow of Ganymede crossing Jupiter. Actually, there is a second shadow there. It's really hard to see on this screen, but there's a second shadow right in the middle, and that's actually the shadow of Io. So that's another moon of Jupiter. So Jupiter has lots of moons, but there were 4 moons that were discovered by Galileo, and they're called the Galilean moons, and they're the biggest and brightest of the 4 moons. Actually, if I adjust the brightness so that you can't see Jupiter's face anymore, but you can see the moons. Oh, let me just adjust this a little bit more this way. You can see a couple of the other, actually if I zoom out, if I move a little bit over, let's move a little bit over. And that's too much. Let's just move a tad over to the left. Whoops, wrong way. The other left. Oops, that's too much. I did the wrong thing. Okay, let me just let's just slew back to Jupiter. I accidentally moved by way too big of an interval. Okay, so there it is. I'm going to move by a smaller interval. But anyways, okay, you can see 2 of the moons here. One of them is Ganymede. Actually, this one's Ganymede and this one's Europa. Why do I know this? Because I checked ahead of time which ones would be out and which ones would be casting shadows on Jupiter. Let me just... Io is actually right in front of Jupiter, and it's really hard to see. Let me move the scale so that you can see the face of Jupiter a little bit better. Okay, there it is. So you can see the shadow of Ganymede is just about to leave the disk. So I don't know if you can see that or not. Isn't that cool? And the other there's a dot right there. That dot is the shadow of Io. So that's pretty neat. I've actually I've seen the shadows of Jupiter's moons cross Jupiter a couple of times before, but you have to catch them at the right point. So you have to look up. Actually, Sky and Telescope has a pretty good app for predicting when the shadows of the moons cross the face of Jupiter. And so you can check every night because Jupiter is really bright right now. Here, let me show you where it is in the sky. It's really bright. It's in the south, so we're looking south right now. It's in the south. It's actually right beside Saturn, which we'll see next. But it's so if you recognize this constellation here, it's Sagittarius. And this little teapot, this it's called an asterism. Actually, a part of a constellation, like a smaller part that is really recognizable, is called an asterism. And this asterism is called the teapot because it looks like a teapot. So right beside the teapot is Jupiter, and right beside Jupiter is Saturn. And Jupiter and Saturn are like the 2 brightest things in that part of the sky right now. Like, you can definitely see them in the middle of the brightest city ever. They're really, really bright planets. So take a look. Go look out your window. Take a look. So this is Jupiter, and that's where it is. And let's take a look at the face of Jupiter right now. And look at that! The shadow of Ganymede. I think that's really cool that we can see eclipses on another planet. Okay, now, I actually have quite a few really cool things to show you tonight. So, if you don't mind, I'm going to move over to Jupiter. So we are looking at Jupiter. We're going to move over to Saturn. But Jupiter, I wanted to tell you, is the largest planet in the solar system. And it has the 4 Galilean moons, as I said, but it's also got a lot more smaller moons. And actually, just like Saturn, Jupiter has a little ring, but you can't see it. In fact, we actually didn't know that Jupiter had a ring like Saturn until we sent a spacecraft over there. And it was a spacecraft that discovered the ring around Jupiter. It's a really thin ring that you can't see at all from Earth, but it also has a ring. Okay, so speaking of rings, let's actually try to look at Saturn. Let's move over there. Okay, so Saturn is a bit dimmer, so we may have to, actually the exposure I think is okay. And there it is, isn't that cool? It really never ceases to amaze me to see Saturn. It's like it's 3D. Here, let me zoom in a little bit so you can see it better. Here, how about that? And there it is. It is a little blurry because of the atmosphere. You can see the atmosphere is causing the image of Saturn to be blurry, but you can tell, look, you can tell that there's a gap right here in the rings. Well, first of all, you can definitely tell that there's, the rings, there's a gap between the planet and the rings, and you can tell that this part is in front of the planet, and the planet is blocking that part of the ring. So it's really 3-dimensional. It's pretty cool. It's like of course planets are 3-dimensional, but you can see it. And not only can you see, you can actually see. You don't need the Trottier telescope to see this. You can actually use quite a really small telescope to see the rings of Saturn. In fact, with good binoculars, you can see the rings of Saturn. It's pretty neat. The rings are huge. They're about the size of the distance between Earth and the Moon. So if Earth was here and the Moon was here, that would be approximately the size of the rings. It's pretty crazy. And yet they're still only like 20 meters thick. They're so thin. They're just made of lots of ice mainly, and that's why they're so bright. It's because it's mostly made of ice. It's quite amazing. And I don't know if you can see, I can see it on my screen. It's hard to see, but there is a little gap in the rings. You can see it here and here near the outer edge of the rings. And that's actually where, that's because there are moons in orbit in the rings. And there's a moon, at least in that gap, keeping that gap kind of clear of ring debris. But Saturn has a lot of moons. Saturn has like more than 80 moons. It's pretty crazy. A lot of moons. Okay, so that was Saturn. So let me just take a look at the chat. Yes, I'm just taking a look at it right now. I can see that there was a lot of problems with the stream, but thankfully things seem to be better. Oh, there was a request to see Mars. Unfortunately, Mars doesn't rise until really late at night. Like, it's not going to get high enough for the Trottier telescope to see until past midnight. So, unfortunately, we won't be able to see Mars today, but we'll probably be able to see it in probably a couple of weeks from now, if the weather is good, it'll probably be high enough for us to see in the later part of an evening. But I looked at it last night. Mars was so cool. You can actually see it's got a bit of a gibbous phase right now. So you know the moon has phases. The moon, so when it's a crescent shape, the dark side is in the shape of a gibbous. So a gibbous is kind of like the opposite of a crescent, right? So when the moon gets bigger, from crescent it goes to half moon, and then it gets bigger than half, and that's also called gibbous. Like it's basically the phase between half and full. So it's kind of the opposite of crescent. But anyways, the Mars was really clearly a gibbous phase. It was pretty neat to see, and you could see the polar ice caps too. But unfortunately, that you have to stay up really late in order to see Mars at this time. But later on in the year, maybe a month out from now, it'll be up a lot earlier in the night, so you don't have to stay up so late to watch it. Okay. So that was Saturn. Oh yes, of course, one of my favorite fun facts about Saturn is that it's less dense than water. So that if you had a gigantic bathtub and you stuck Saturn in it, it would float. Isn't that crazy? It just blows my mind. So it's got over 82 moons. And that number keeps growing. It seems like when I was a kid, I think I remember it having something like 27 moons or something like that, and I memorized. I was really keen on like astronomy and the planets, and I memorized all these facts. But it was no use because those facts kept changing all the time. So, but that's science, right? Science keeps progressing, and we keep improving our knowledge of things. So now we know, at least for now, that Saturn has something like 82 moons, and that number could go up too as we send more spacecraft or as we have more powerful telescopes and we see more things. Okay, so those are the two biggest planets in our solar system, and we are going to now leave our solar system and take a look at a few other cool objects in our galaxy. Okay, so what is the solar system and what is the galaxy? So the solar system is made of our planets. So it's the sun and all the planets. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, etc., etc. So, and also the asteroids and the comets and, and the minor planets. All of that belong to the solar system. Now the solar system is really tiny compared to our galaxy. Okay, so our galaxy is made of something like 100 billion stars, like our sun. And stars are born somewhere. So where are stars born? So that is what we are going to see next. All right. So I wanted to show you a really cool nebula where stars are born. Called M17, the Swan Nebula, or also known as the Omega Nebula, and you'll see in a minute why it's called the Swan Nebula. I think it's really cool. It's a very, very pretty nebula. Okay, but I have to change my profile so that it is taking longer exposures. There we go. All right, now, where are we? 20 seconds, and I'm going to live stack. So what this means is that we're going to be combining like a bunch of images together in order to make a better image. So let me just adjust this image while it's going. Too much red here. It is a very, very red nebula, but it was a little bit too much here. Okay, there we have it. Isn't that pretty? This is the Swan Nebula. Now, why is it called the Swan Nebula? Maybe you can already see it. It is you have to turn your head a little bit to the side in order to see it. But this is where I see this swan. Okay, it's kind of upside down. I would see this as the neck, and this is the body. So you kind of it's kind of turned around a little bit. You have to turn your head to see the swan. But I think it looks so cool. It's actually one of the brightest nebulae in the sky that you can see. So this one you could probably find with your you could probably find with your telescope. Now where is it in the sky? This is so it's still in Sagittarius. So a lot of the star clusters and like open clusters, okay, I'll get to that in a second, but a lot of the nebulae in our sky are in the Milky Way, because the Milky Way, as I said, is a big, huge group of about 100 billion stars, and all those stars are situated in a bit like a plate, like a disc, like a frisbee, and we're in the middle of it, and it's the thick, like we're much tinier than the thickness of the Milky Way. So we see stars all around us. But when we look towards the center or towards the edge, then we see a thicker concentration of stars, and that's where it looks a little bit brighter than the rest of the sky, and that's what's called the Milky Way, because it looks a bit milky. And so the center of the Milky Way is actually in Sagittarius. And the Milky Way goes from Sagittarius to Aquila the Eagle, to Cygnus the Swan, over to Andromeda and Perseus. Actually, the Perseid meteor shower, I should talk about that too. But in a second, I'll talk about the Perseid meteor shower in a second. But the Milky Way goes all the way through here, and that's where most of the pretty objects, like the nebulae, are found. And so that's where we're looking right now. This is where the Swan Nebula is, kind of just above the teapot right there, very near the center of our galaxy. The center of our galaxy is approximately in this area of the sky. Okay, let's look at the nebula. We came to look at pretty pictures, right? So this is the Swan Nebula, and it's enormous. It's really big. It's just a second. It's about 15 light years across. So remember, the distance from the sun to the Earth is 8 light minutes. Okay, so this is 15 light years across. In fact, we're only seeing part of it, actually. It's quite big. It's about 5,000 light years away. So it's quite far. I mean, well, it's in our own galaxy still, but it's towards the center of the galaxy. And it's one of the youngest known nebulae, I should say. And this will come from Latin, and that's the plural. And it's about 1 million years old. Now there are 2 stars right here that are what are known as hypergiants. The brightest one, it's pretty crazy, the brightest one is 400,000 times brighter than the sun. It's crazy. Isn't that crazy? That's like huge. Our sun is already really bright. Imagine being in orbit around that star. Right, yeah. So the other one, this hypergiant right here, apparently it looks a lot like the star that went supernova in 1987 that was inside the Large Magellanic Cloud, which was like a satellite galaxy around our galaxy. You can't see that galaxy because it's in the southern hemisphere, so you can't see it from Canada. But if you went to South America or Australia or New Zealand, one of those places, you could see the Large Magellanic Cloud. It looks like a cloud, but it's a galaxy that's in orbit around our galaxy. And in 1987, there was a supernova in that galaxy from a star that looked exactly like this one. So maybe it'll supernova us at some point. I don't know. I mean, it's soon in astronomical terms can be millions of years from now. So it might be a while, so don't hold your breath. But this is an example of a nebula in which new stars are born. So stars this is a nebula that is a stellar nursery. So it's one example of a stellar nursery. And so there are a lot of these in the Milky Way, actually. And there's another one I want to show you. It's not as bright as this one. But this is one of the brighter ones. This is the swan nebula. Isn't that pretty? Look at that. So it's stacked pretty well. I'm going to adjust the image just a little bit more and save it because it's pretty. Not quite. So yeah, you can play around obviously with the color, with the lighting, and then snap a shot of this. So pink. Why is the nebula pink? So the most abundant element in the universe, can anybody guess what it is? The most abundant element in the universe. Who can get it? H! Godwin says H. Yes, hydrogen. That's right. Hydrogen is the most abundant element in the universe. Oh, and Jennifer said so too, and several people did. Oh, perfect! Lots of people got it. Hydrogen, yes, it's the most abundant element in the universe, and it glows in pink. So if you see pink, then it's most likely hydrogen. So we're going to see a few other nebulae, and you'll see pink in some of them, and you'll know exactly why it's pink, because it's hydrogen. So actually stars are mostly made of hydrogen, actually, and so basically most things are mostly made of hydrogen. Okay, so there is blue as well. Lots of nebulae are blue, but they're mostly, the blue, we'll find out, is from oxygen, which is made inside of stars. And so you don't really see them as much in stellar nurseries, but you do see them in nebulae that are the remnants of stellar death. So because oxygen is made inside of stars. Okay, so that was the Swan Nebula. Very pretty. Let me take a screenshot of that. And I'll save it. I'll save it in all its forms. Save with adjustments, save exactly as seen. Okay. And also I'm going to take a selective screenshot like this. Yes. Excuse me while I save this in a new folder. Perfect. Okay. So that was the Swan Nebula. Let's see. Any questions? Yes, Orion has blue and purple. Yes, that's true. Yes, it does. It does have a little bit, but yes, it does. It does. Yeah. Hydrogen. So all nebulae, including planetary nebulae, are like over 90% hydrogen. So any kind of other elements that you might see that cause other colors, or even though they might be quite bright, they actually represent only a tiny fraction of the mass in the nebula, in the cloud. But let's take a look at, what time are we at? Okay, let's take a look at M16, just next door. So the Swan Nebula was M17. What does M stand for? M stands for Messier catalog. So M17, and we're going to go to M16, which is the Eagle Nebula, which is very pretty. But this one is not as bright, so, but you can see the outline of the pillars, which is pretty cool. So I'm going to show you that. So let's clear this and start again. So let's see. Okay, oh, the other planets are also actually rising quite late in the night. Oops, let's see, it was still moving. Let's clear that. And let's do it again. They rise quite late in the night, so we won't be able to take a look at the other planets, unfortunately. And anyways, they only appear like little dots on the screen. They're not terribly impressive, unlike the nebulae that we're going to see. So this is another star-forming region. You can, as the picture gets, as the frames stack, so we're taking 20-second exposures, 20-second images, and we're stacking them together. So it's doing this app is doing this automatically. I'm using SharpCap which is a great little app for automatically combining images. So that's called stacking. So we're combining the images so in order to get a clearer, brighter image. It's not going to get that bright, but we can adjust it a little bit so that you can see it better. Let's try moving it. Whoops. No. This way. And let's move this down a bit so you can see more. Do you see the pillars? You can start seeing the pillars. It's so cool. I think the pillars just get me every time. This was the Hubble Space Telescope was launched in '93, and very shortly after, I think they discovered there was a problem with the optics, so they had to send up a team of astronauts to fix it. I actually know the scientist that figured out what was wrong with the telescope. That was actually, not an easy thing to solve, and I know the scientist who figured out what the problem was and told NASA how to fix it, so they fixed it. And shortly after that, the Hubble Space Telescope had released this gorgeous image of the Eagle Nebula, where these basically focused on these three pillars here. And those pillars, the image was called the Pillars of Creation. It's a very famous image from that era. And I was a little kid at the time. Please don't try to calculate my age, but there we go. I was a little kid at the time, and it was so amazing. It was really inspiring to see that image of the pillars of cloud being lit up by some of these stars. So these stars here in this corner are really young, bright stars. Some of them are actually hypergiants. I don't actually know which ones, but they're really massive, bright stars. And these stars are shining down on the pillars, and that's why you see light on this side and dark on this side. It's because it's light from those stars, actually. And those stars give off a very powerful wind. So just like the sun gives off a solar wind, and it's because of that wind that we get the comet tails. So we remember that we saw Comet Neowise last month, and it has a tail, and the reason is because the solar wind is blowing that tail. And the solar wind is also responsible for the northern lights on planet Earth. And this is all stars. So the sun is a star, and all the stars give off a bit of a wind. And the more massive you are, like the bigger the star, the more powerful your wind. So the winds from these stars are actually sculpting the pillars. And so it's actually blowing the pillars away. And eventually, the nebula will dissipate and will be will disappear eventually. So and then you'll be left with just a cluster of stars. So this is a cluster that is being formed in this nebula. So this is another example of a stellar nursery. Oh, I wanted to give you a few little facts about how big this nebula is. So that the longest pillar is something like, it's almost 10 light years long. It's pretty crazy, really big. There's thousands of young stars in this cluster, something like 8,000, and it's pretty young. It's about 6,000 light years away, and the brightest stars are the most massive, obviously. Yeah. So that was the Eagle Nebula. So somebody says it looks like a person in a robe with two arms. Yeah, it could be, like Gandalf maybe, I don't know. It's pretty neat. So that is the Eagle Nebula. Let me see if I can adjust the image a little bit. Oh, again, what color is it? It's pink, right? And we all know why that is. Because it's hydrogen. So you probably all said that, didn't you? You all shouted out, it's hydrogen because it's pink. It's perfect. We're gonna make scientists out of all of you yet. Okay, so that's all right. I'll take a screenshot of that too. It's pretty. Save. do one more of these as well. Okay, cool. So that was Eagle Nebula. And okay, so what's next? Okay, so I did say that so stars are born in such nebulae, big clouds of gas, and you need gas in order to form a star. So what happens then when the winds blow all the gas away? Well, then you just get a cluster. So I'll give you an example of it. We can look at the wild duck cluster. I think somebody actually requested that. Wild duck cluster. It's right there, so nearby. So remember, all the clusters and pretty nebulae are really close to the Milky Way. They're all basically all in like the milky part of the Milky Way. When you look in the sky, when you go camping and you look at the stars and you see this white thing, the huge white thing that goes all the way across the sky, that's the Milky Way. And that's, if you point a telescope at the Milky Way, you'll see lots and lots of stars and nebulae and clusters and star clusters. So this is a star cluster. It's called an open cluster. Open because they're not gravitationally bound. Oops. Opened the wrong app. Excuse me. Okay. Ah! I clicked on it again. Okay, here we go. Let's clear that and start again. Let's clear that. Telescope is still moving. So this is an open cluster. And so clusters of stars are born from the same cloud, just like the Eagle Nebula or the Swan Nebula. But they're old enough now that that the stars have kind of blown away the nebula. So you're left with just a star cluster. Now, this open cluster is not gravitationally bound. So eventually, as the stars orbit the center of the Milky Way, they'll eventually drift apart, and they'll go on like their own separate ways. Their orbits will separate them. So this is an example of a cluster. Now, why is it called the wild duck cluster? So apparently, somebody looked at this, and you can see in this image, you can see a lot of stars, but the brightest ones make a V pattern. I think it's these ones, the brightest ones, and so it kind of looks like, wild ducks, or Canada geese or something, flying in a V shape. So that was the reason. But of course, there are a lot more stars in this cluster than just those brightest ones. So you can see them right here, and you can see some of them. You can see different colors in here. Some of them are red, and some of them are white. The redder ones are going to be most of the red ones will be like the least massive ones, and some of the red ones will be red giants as well. But actually, with the age of this cluster, probably not. They're probably going to be mostly low mass stars. So when stars are born in a cluster, they're all born together. Pretty much more or less, right? Give or take like a million years is not really a big deal when that's basically born at the same time. So they're born at approximately the same time, and they're all born together. And so they're clusters of stars are born in such a way that there are very, very few of the really massive stars, but there are lots of the really little ones. So that's how they're born. And in a cluster, you're going to see lots and lots of little ones and very, very few of the small ones. It's just kind of how gravity works, how a cloud kind of collapses under its own gravity to make stars. It's kind of worse. It just kind of produces this pattern of a lot of little ones. So you can actually see a lot of little ones in this cluster, a lot of little dim ones. So the fact that they're in a cluster means they're roughly the same distance from us. So, a few 10 light years, that's basically compared to like 6,000 light years away, it's basically the same distance. So if you see a dim star in this cluster, it means it really is dimmer. It's really a smaller star. And the brighter ones really are brighter. It's not that they're like closer or farther from us, because they're roughly the same distance if you see them in a cluster like that. So star clusters are really important to understand stellar the stellar life cycle and that kind of thing. So this is an example of an open cluster. Okay, so this is what happens when the nebula kind of dissipates because of the stellar winds blowing them away. Okay, cool. Great, a lot of great questions. Thank you again to Matthew, Sarah, and Zena for taking these questions while I'm playing around with the images. All right, so now we're going to we looked at nebulae, which are sites of stellar birth. Now we see some, like a middle stage where the cluster has just blown away its nebula, but they haven't spread apart yet. And now we're going to look at some very pretty nebulae that are the sites of stellar death. So that will be really fun. Which one should we start with? Actually, there are so many. I don't know if there are so many pretty ones. I don't know if we'll have time to look at them all. But let's see. I think let's go to something called... There's so many of them. So I have on my list a bunch of potentials that I've looked at ahead of time to make sure they show up well enough in this camera, and there's so many of them. They're very, very pretty. I had so much fun last night actually looking at different objects. Okay, so I am going to start with something called the Cat's Eye Nebula. It's small, so we won't have very good resolution on it, but it is quite bright, and it's got some pretty cool facts about it. So it's up very high in the sky right now. It's all the way in Draco. So this is the constellation of Draco right here. This is the Little Dipper, that's the North Star. If I move over there to the north, you can see it a little bit better. There we go. So there is a Little Dipper, that's the North Star above north. So in Canada we are approximately 50 degrees north latitude here in Vancouver. And so actually the position of the North Star, so if you measure in degrees, so if you look at the horizon, you stretch your arm out horizontally toward the horizon, that's like 0 degrees, right? And if you stretch your arm up right straight vertically above you, that's 90 degrees from the horizon. And so 50 degrees is approximately how high the North Star is above our horizon here in Vancouver. So actually, and you can, if you're in the northern hemisphere, that's approximately how you can tell, whatever your latitude is, the North Star will be that many degrees above your horizon, above the northern horizon. Okay, so let's actually look at the nebula. So the Cat's Eye Nebula, we're going to need to actually take, we're going to need to zoom in on this because it's really small. It's something called a planetary nebula because it's round, so these are remnants of stellar death, and so they're round, and so the early astronomers thought they looked like planets, and so they called them planetary nebula because they look like, when we saw Jupiter and Saturn, they're about that size, and they're round, like Jupiter's round, right? So they look like a disk. And so that's why the early astronomers called them planetary nebulae, even though they have nothing to do with planets. So unfortunately the name has stuck. Oh, there it is. Wow. So cool. Okay, so let me adjust the image a little bit before I talk a little bit about it. Okay, I'm going to have to adjust, in order to see more detail, I'm going to adjust this level, the mid-level, up a bit. Isn't that cool? This is the Cat's Eye Nebula. So, So it's kind of like, because somebody who looked at it thought it looked like a cat's eye, kind of like the Eye of Sauron, right? So I don't know if you can tell, but I'm a big Lord of the Rings fan. So that's the Eye of Sauron, but actually it's called the Cat's Eye Nebula. So there are lots of cool, interesting things about this nebula. So it's, again, this is a nebula that is the site of stellar death. So actually we can't see it, but there is a lot more nebula outside it. It's just really, really dim. You need like the Hubble Space Telescope to see it. It's really, really dim. So the outside is when the star, before, like right now, it's basically almost a white dwarf. But before this stage, it was a red giant. So when it's like the sun isn't a red giant, it's just a normal star. When it's burning hydrogen like a normal star, it just burns hydrogen and turns it into helium. And then once it runs, like, it only does that in the core, not in the whole star. Right inside the center of the star, it burns hydrogen into helium, and then once it runs out of hydrogen in the core, then it starts turning helium into heavier elements like carbon, nitrogen, and oxygen. Once it really runs out of fuel, then it expands into what's called a red giant. And when it expands, eventually the outer layers of the red giant float away, and so they're actually out, that you can't see them. But the winds from the star continually blow out more layers, and sometimes they collide into the outer layers that were floating away slower. So sometimes you see these pretty patterns here. So this nebula is a little bit more complicated than that, because what people have discovered is that it's probably actually a binary system, meaning there are two stars in orbit around each other. Where this is actually one of the most popular theories about this nebula, where the two stars are so close together, such that one of the stars is sucking away material from the other star into a disk. Like the material doesn't go into a straight line into the other star. It actually spirals in a bit of a disk around the star before it eventually lands on the other star. So that a disk is called an accretion disk. It's a disk. Okay, just think of it as a disk. And a disk like that often gives off a lot of energy, but because there's like a disk, there's material in this disk, then the energy, the material, it's hard for it to go out horizontally. It's much easier for the material to go out the poles, so go out on above or below the disk, the plate, So what this leads to are jets that stream up and down instead of like through the disk. And so, but these polar jets, they twirl around, just like, actually, I don't know if you knew this, but the rotation axis of the Earth is also twirling around. I don't know if you knew, but it's something like every 26,000 years, the axis of the Earth rotates. And that's called precession. So for the same gravitational reasons, because of gravity, the gravity between the moon and the Earth and the sun, and that's the reason why the axis of rotation of the Earth wobbles a bit. For that same reason, the polar jets around the disk around that star are also wobbling, and that wobble causes the spiral shapes around the nebula. Okay, so that was really long-winded description of the best theory we have so far of why this nebula has the shape it does. You can't really see it here, but there is a little bit of a spiraliness on both sides of this nebula. And you can see that there's pink on the outsides, because pink is wet element. Pink is the most abundant element in the universe, and it is hydrogen. Thank you, Ronell. And blue. Okay, I mentioned it earlier, but what is blue? Blue, it's actually kind of blue-green. What element is blue-green? Does anybody remember me saying that? I kind of said it in passing, but if you've been to some of these other starry nights, I've said it before. Oxygen! Yes! Yes, very good. So blue-green is oxygen, and actually a lot of these planetary nebulae show really, really bright oxygen. And the reason is because, as I said, stars turn hydrogen into helium and then helium into heavier elements like carbon, nitrogen, and oxygen. So oxygen is made inside of stars. So the conditions are just right so that the oxygen shines very brightly. Even though actually 90% of the nebula is made of hydrogen, to be honest, and only trace amounts are, and the rest of it is almost all helium. But there are trace amounts of lots of other elements. Now, when I say trace amounts, okay, remember this star is probably something like the mass of our sun. Trace amounts still means like bigger than Earth. Okay, so there's still a lot of oxygen. So actually all the heavier elements on our planet and in lots of other planets are actually made inside of stars. It's pretty neat. So that's the Cat's Eye Nebula. Oh, I keep going on and on and on. Now there's still more I wanted to show you. Is the bright spot and the dominant star. Yes, so they're probably so close together, like they are so close together that you can't actually distinguish them. Okay, so that was the Cat's Eye Nebula. It's very, very cool. I wanted to show you a few other things too. Maybe I can show you, okay, I'm going to show you one that is really blue. This is called, in fact, it's called the blue snowball. So where is it? This is Pegasus, but I believe it's actually officially in the Andromeda constellation. The blue snowball is actually quite bright. And again, it's a planetary nebula, so it's about the size of a planet, so you do have to zoom in, just like we had to zoom in on Jupiter. We have to zoom in on this planetary nebula, just like we did with the Cat's Eye Nebula. And it's pretty cool. I forgot to mention that, oh, okay, never mind. Okay, the blue snowball, it's pretty cool because it's like almost completely, actually I shouldn't talk, I'll just show it to you. Oh, I need to save this image first before this is really pretty, so I'm going to save it. And okay, that's probably enough. Okay, clear that, and let's see the blue snowball. Okay, here it is. Isn't that cool? This is actually, it's really blue. It's really quite blue. There is a lot of hydrogen in this nebula as well, but the oxygen is, so, okay, for those of you who really want to know the physics behind this, oxygen is, so oxygen has, what, 8 protons, right? And so normally it would have 8 electrons, but the fact that the winds from the star are pushing the gases around so hard makes the oxygen atoms collide with other atoms, and in so doing it loses 2 electrons. When the oxygen loses 2 electrons, it loses 2 electrons only temporarily. The 2 electrons eventually come right back down and combine with oxygen again. But when the electrons come back, they give off this really particularly greenish blue light, and that's why we see oxygen. Now hydrogen, this hydrogen, you can actually see in this image a little bit of pink across the image. It's because the outer kind of sphere around the nebula is hydrogen, and so you can actually see it. But the insides are glowing pretty brightly in oxygen, because the inside, because that's where most of the oxygen is. It's in the inside, because they're formed in the cores of stars, and this star is dying, so it's giving off its layers, outer layers first, then the inner layers start coming out. So this is the blue snowball. Let me adjust this image a little bit, but it's pretty. It's like, it doesn't really need a whole lot of adjustment, does it? Let's see. Okay, well, let's let it stack a little bit. Okay, so, right, somebody asked, I think I glanced at the live chat and saw somebody was talking about, that's right, stars can only burn up to iron, and then after that, the heavier elements are from other processes, such as supernova explosions, as well as neutron star mergers. Those neutrons, so a star that's made of only neutrons, rich with, so there are protons and electrons and neutrons. And neutrons, you need a lot of neutrons in order to make the really heavy elements. So the only process that we know of capable of making those elements is actually neutron star mergers. So, oh, what is this one called? This one is called the Blue Snowball Nebula. Isn't that funny? It has an actual designation. I think it's like NGC 7662 or something like that. But we can. It's easier to remember the Blue Snowball Nebula. All right. What are we at right now? That's the Blue Snowball. Isn't that pretty? Okay, I'm going to take a few pictures of this as well before we move on. There are a couple of, I just have a lot on this list, and I wanted to, we don't have to see them all, but it's just fun to see them. So, once again, what is a planetary nebula? A planetary nebula is the site of stellar death. So the star has finished burning most of its fuel, and the layers of the star are just coming off, and it's turning into a white dwarf. So a white dwarf is just the end product of a star. So our sun will probably turn into a white dwarf. In fact, our sun will probably turn into a nebula like that as well. Maybe one closer to another nebula that we will see. But yeah. So planetary nebulae are the sites of stellar death. They tend to be quite bright but small, so you can't really. Again, this is just digital zoom, right? So this is not. We just zoomed in on the picture, so you can't really see it as clearly as, the Hubble can. But I did zoom in on it, so you could see some detail, like this inner ring here, and some of the pink over here. There's some pink on the edges as well. And but yeah, you need to zoom in like you would on a planet, and that's why they're called planetary nebulae. But there is at least one or two one that is quite a bit bigger than a planet on the sky. Just like, they're much bigger than planets, of course, but kind of on the sky. It looks quite big, which we'll probably get to see. But first we'll see... Oh, did I save them all? I did. Okay, I'm going to take one screenshot of that. And I'll do this kind of screenshot as well. Very, very pretty. Okay. Okay, so what are we at? 11. Okay, we're actually doing not too badly with time. Okay, I am going to show you, I know I've shown this in the past, so some of you who have been on this before, you'll have seen it, but I think it is so pretty. It's called the Dumbbell Nebula, and this one is one of the ones that's bigger, so I'm going to zoom out, and it's got a lot of color in it, which is why, by the way, notice that we've gone through the Milky Way. So the Perseus, oh yes, I need to talk about the Perseid meteor shower. Why don't I do that before I'll have to jump back to the solar system in a minute. But this is Perseus, Andromeda, the Cygnus the swan, and Aquila the eagle, and so the Milky Way kind of goes along here. So we saw the Dumbbell Nebula here, we saw the blue snowball here, and we saw the Cat's Eye Nebula was actually over here. So this one was actually off the plane. I mean, it's in the plane of the Milky Way, it's just closer to us. But most of them are here. So, and we saw the Swan Nebula over here, we saw the Eagle Nebula here. So they're all along the Milky Way. Most of them are along the Milky Way. So I was going to tell you, I didn't want to forget, but unfortunately we can't really, like, the best way, actually this isn't unfortunate, this is really good. The best way to view the Perseid meteor shower, is a meteor shower if you like take this like a time-lapse photo, you'll see that they're mostly coming from the constellation of Perseus. This is Perseus right here. And so they'll all be kind of radiating out from it. Now, the best way to view a meteor shower is actually with your own eyes. So you should be looking, just go out onto your lawn or onto a hillside or something where you can see a good portion of the sky and just watch. And you can see shooting stars all over the sky. So you can't really see shooting stars very well with a telescope. So unfortunately, we're not going to be looking at the Perseid meteor shower with a telescope because they, they're huge things, and you don't need a telescope to see the Perseid meteor shower. The Perseid meteor shower is like remnants of debris from a comet Swift-Tuttle, and it happens every year. At the peak of the meteor shower happens around August 11th, August 12th. And so that was a couple of days ago, but you can still see the meteors for a week before and after at the peak. So you'll see the most shooting stars on the 11th or 12th, but you'll still see a lot of shooting stars before and after that date. So yeah, if you have a chance, take a look, maybe even this weekend. The best time is after Perseus rises, but it's so around midnight or so, and afterwards. That's the best time to be watching a meteor shower. But you don't need to stay up that late. You can watch it earlier if you want. Okay, so yes, I talked about the Perseid meteor shower. Good. Now let's go over to the Dumbbell Nebula. Yay! Let's clear that and let's look at it. So the Dumbbell Nebula is another planetary nebula. But, I forgot to change the profile. I'll have to zoom out. Zoom out. And, okay, let's clear that and let's take another image. The Dumbbell Nebula is quite a lot bigger on the sky because it's closer to us. It's not because it's actually bigger. Like, it's like 3 light years big, and all planetary nebula are about that, between 1 and 3 light years. Ish. I mean, they can get a little bigger too, but for the most part, so the reason why this one is bigger is because it's closer to us. So there it is, and we'll just let that stack a little bit too. It's also called the apple core nebula because it looks a little bit like an apple core, right? So, this is the top and this is the bottom of the apple core, and somebody has eaten out the center of it. It's kind of neat little picture. So this is a planetary nebula, and here you can really see the difference in colors in this nebula. So you can see pink, which I've said before, and we all know now is hydrogen, and then there's the bluish green, which is oxygen, and it's in the center because that's where most of the oxygen is found, in the center, because it's formed in the core of a star. And so the hydrogen layers, which are on the outside, get blown away first, and then the oxygen gets blown out later, so that's why they're mostly in the center of the nebula. But again, as I said, if you take up all the mass in this cloud it's going to be something like 90% hydrogen. And but oxygen glows very brightly because the conditions are right in this nebula for the oxygen to glow. Yeah, so this is the dumbbell. It's very pretty. It is, so yeah, it's about 3 light years across. And this one, so it is closer to us, and the other ones were a few thousands of light years away. This one's more like 1,200 light years away. Again, the shape of this, so it's kind of like this, the material from the star has kind of blown out in 2 directions, and this is probably because of a disk of material around the star. So it's a single star, it's not a binary, but the disk of material, you know, whether it's like asteroids or like you know, other kinds of material, it's probably bigger, much bigger than the asteroid belt. But this disk of material is blocking the gas in these directions, but so that's why the gas is mostly able to escape from these 2. So that's kind of one reason why astronomers think these nebulae have these shapes. But like the truth is, it's not really well known why these nebulas, why any of these shapes are the way they are. It's not really that well known. These are kind of best educated guesses as to why the explanation for these disks. So this is so inside the central star here is a white dwarf, and it's probably what our sun will eventually become in something like 5 to 8 billion years. So you don't have to worry too much about that. It will take some time. Yes, so this is the Dumbbell Nebula. Okay. I have a few more. We have 20 minutes. I have a couple more things I wanted to show you. We are getting through a lot of things tonight. This is really fun. Yes, by the way, some of these halos here are what's called light pollution. Oh, that's right, I turned off the images of the observatory. But if you look at the images of the observatory, there's actually a really bright light in a spot close to the observatory, and that bright light is causing these little halos, unfortunately. What can you do? We're on campus in the middle of a city, and safety also matters, not just astronomy. So sometimes we just can't look in certain directions, but what can you? We can still see the nebula, so it's not so bad. But yeah, I would have shown, if I had that camera on, I would have shown you exactly where that light is. You can see it in the camera, actually, the webcam. Yes. All right. Okay, let's move on. That was a dumbbell. Very pretty. Lots of different colors. It's nice to be able to see the colors. This camera, by the way, this is a color camera. And it's not as sensitive as our good camera, which is in black and white, but it's in color, so you can see the colors right away. So the black and white camera that we have, in order to take images and make color out of it, what you have to do is put color filters in front of the camera, and then so you do a red filter, and then a green filter, and then a blue filter, and you combine the images later. So it takes some processing after the fact. So that's why we're using this color camera, even though we can't see the details that well, at least it's in color. Okay, so let's take a look at, so we saw a lot of nebulae, which are really fun. One thing I wanted to show you, is it up high enough yet? I think it is. Oh, it's a little bit low. I was planning on showing this M33 at the end of the night. Let's see how high it is. It says it's 23 degrees. That's actually not too bad. Wait, let's do it. So M33 is a galaxy. It's a very interesting galaxy. Now, galaxies are actually my specialty. That's what I study, is galaxies. So I know that when you think of an astronomer, you like to, like, a lot of people ask me about planets, about nebulae, and I love nebulae. They're really pretty, and planets are fun too. But the truth is, you know, planets are so different from what I study. Planets are like, you know, like galaxies are way, way bigger. It's like somebody who's like, you know, a biologist, and maybe they study the human body, and you ask them about like the physics of hydrogen atoms. Like, human bodies are made of hydrogen, but you know, that's not really it's not really what a biologist studies, right? So galaxies are way, way bigger than planets. Planets are like little tiny specks of almost nothing, right? Of course, the planets are everything to us. We live on one. It's the, you know, it supports our life. But galaxies are much bigger. They are, again, as I said, our Milky Way is about 100 billion stars. And the this galaxy that we're about to see is smaller than that. It's like, I think it's something like, it's more like 10 billion stars. I think it's about one, or yeah, it's something like that. We're 100 billion stars. I think it's about 10 billion stars. It's a smaller one, so it's a bit of a, it's kind of a dwarf galaxy, but it's actually, let's look at it while I'm talking because that would be much cooler to do, wouldn't it? Okay, so it's kind of a dwarf galaxy that is, but it's kind of halfway between a dwarf and a giant, and it's in orbit around the Andromeda galaxy. Okay, let's adjust this image. It's pretty cool because you'll be able to see when I adjust this image, you'll be able to see within this galaxy. So a galaxy is huge. Galaxies contain nebulae like the ones we just saw, and you'll be able to see once. Actually, you can see one already right here. But when this image stacks a little bit better, you'll be able to see it a bit more clearly. But you'll be able to see that this galaxy actually has a lot of nebulae. So this is quite far away. I don't remember exactly how far away it is, but Andromeda is about 2 million light years. So M33 can't be that far off from that. And it is, so this is M33, M for messy again. It's a spiral galaxy. It's really beautiful spiral arms. And inside the spiral arms, you can see a whole bunch of star-forming regions. Soon as we can get this thing to stack. I wonder if this will help to enhance the image. Okay. This won't be as impressive as the Andromeda galaxy. The Andromeda galaxy is much brighter than this, so we can look at this after. We can look at the Andromeda right afterwards. But this one, I wanted to show you this because we just finished looking at a whole bunch of nebulae, and now we can actually see nebulae in another galaxy. It's crazy. So that one's starting to get brighter now. You can see that is another star-forming region. So that's not a planetary nebula. A planetary nebula would be much smaller. So an actual like a star-forming nebula will be tens to hundreds to even 1,000 light years across. No, not really. Actually, the biggest one is something like the biggest nebula we know of is actually in this galaxy. It's not quite in this image. It's near, I think it's this direction somewhere. It's not this one. It's another brighter one here. But in any case, so maybe tens of light years is a typical size for a star-forming nebula, but a planetary nebula is more like 1 light year across. So it's harder to see the planetary nebulae in another galaxy, but you can see star-forming regions like this one. And the star-forming regions, scientists call them H2 regions. I know it's a funny name. You don't really have to know, like, you don't have to memorize it if you don't want to, but it's a fancy name for star-forming region. It's basically what it is. Whoops. Okay, let me try to adjust this a little bit more. And it's hard to see. Okay, let's just bring this over here. Okay, it was easier to see the other night, and I'm not sure. Oh, I know why. I know why, because I was up late looking at this galaxy and it was up higher in the sky. So when you're really low in the sky like that, this is in the east, so it's going to rise, so it's going to get higher and higher in the sky, and when it gets higher in the sky, then you have less atmosphere to look through, and we're in the middle of a big city, and the atmosphere is quite bright when it's, you know, especially closer to the horizon, so that's the reason why it's not very clear. But we'll move in a second to the Andromeda galaxy, so don't worry about it. We'll still get to see another galaxy. But I just wanted to show this to you so you could see star-forming regions in another galaxy. I think it's kind of neat. Oh, we only have 10 minutes left, actually, so maybe I should move on to that. But let me just make sure I don't want to miss any important questions. Looks like my helpers are doing a great job answering these questions. All right. So the Andromeda galaxy will be a lot brighter than this, so we can move on to that one next. Oh, but I forgot. Okay, no, another cool fact about this galaxy, M33. It was quite big news when it came out. But this galaxy seems not to have a black hole in the center of it, which was very, very weird. So we think that most galaxies in the universe have this massive, really, really massive black hole in the center. Actually, they're so massive we call them supermassive black holes. I kid you not. We really call them supermassive black holes, and we abbreviate that by saying SMBH. Supermassive black holes. Hey, we're not known for our creativity in naming things in astronomy. But in any case, our supermassive black hole in the center of our galaxy is about 1 million solar masses. So there is one in our center, and you can measure the mass because you can actually see the stars rotating around it and orbiting around the black hole. And you can just apply Newton's laws, you know, from high school physics, and you can calculate the mass that's in the center. And since it's not shining any light, then you know the only thing, it's 1 million solar masses. So the only thing it could be is a black hole. So that's how we know that there's a supermassive black hole in the center of our galaxy. And we were able to recently see a picture, actually create a picture of a black hole in the center of another galaxy in the Virgo cluster, M87. So this galaxy, surprisingly, some scientists in about 2001 or so measured the motions of the stars in the center of this galaxy and found that the motions were so slow there couldn't be a black hole there more massive than, I think they had an upper limit of 3,000 solar masses. So their instruments weren't sensitive enough to detect anything smaller than that. 3,000. So 3,000 sounds like a lot, but it's actually nothing compared to 1 million solar masses, which is what's in our galaxy. So it's pretty crazy that they weren't able to they didn't see anything in this galaxy. So this one is famous for seemingly not having a black hole. And so there are a bunch of different theories as to why it doesn't have a black hole, and whereas everybody else does. And it might be because of interactions that kicked the black hole, because of gravitational effects. The black hole got kicked out of the galaxy through some orbital things, orbital dynamics, and maybe it experienced a merger with another galaxy, and the dynamics of the black hole interaction kicked them both out. So that's one of the theories as to why it doesn't have one. But yes, that's M33. So this one is not as impressive as I wanted it to be. Okay, let's move on to another galaxy then. M31, which is the Andromeda galaxy. So we can spend our last 5 minutes on that, which is just next door, which makes sense because M33 is in orbit around M31. M31, which is the Andromeda galaxy, is actually visible to the naked eye. If you're in a really dark spot, out camping or something, you can actually see the Andromeda galaxy with your naked eye. It is the farthest object that we can see with the naked eye. It's about 2 million light years away. It's pretty neat. And it's so big that it like we're only going to see a tiny fraction of it in our camera. It's way bigger than, in fact, it's like it's huge. It spans, so you know, most things are really tiny, you have to zoom in, but this thing spans, it's probably going to be at least this big. It's quite big on the sky. Wow, there's the center of it. That's the center of the Andromeda galaxy. Let me show you a bit more. And there it is. Isn't that pretty? So this, you can see the dust lanes as well in the Andromeda galaxy. Wow, it's so pretty. There it is. So this is the Andromeda galaxy. Yeah, so the Andromeda galaxy is about twice as massive approximately than the Milky Way, so it is more massive than us. And the two of us, so the Andromeda and the Milky Way, are the two most massive galaxies in what's called the local group of galaxies. So, the Andromeda galaxy and the Milky Way, we have, you know, between us about 40 dwarf galaxies orbiting us, and yeah, the Andromeda has some, and we have some, and we're orbiting in such a way that eventually the Andromeda will actually collide with the Milky Way. That will happen in about 5 billion years, about the time when our sun is about to die. So, but it doesn't matter though, even if our sun continued to live beyond that, the collision of the Andromeda galaxy with the Milky Way actually wouldn't affect anything on the Earth, because there's just so much space between the stars that the likelihood of stars colliding because of the merging of the galaxies is actually really small. So life will just go on as normal, but we'll see, like, there'll probably be, so if anybody remains on the Earth at that time, they'll probably just see a brighter night sky with more stars. So that's most of what will happen. Yes, and the merger of the Andromeda galaxy and the Milky Way is sometimes called Milkomeda, which is kind of a funny little thing. Yeah, so that's the Andromeda galaxy. So, how many stars are there in this galaxy? It's about twice as massive as the Milky Way, so it's probably about twice as many stars. So, you know, everything in astronomy is very, like, a round figure. It's all estimates. So I said 100 billion, but it's like, you know, that's basically the same as 300 billion. You know, 1 and 3, it's not a huge difference in astronomy. And then, and whatever it is, it's probably about twice. And maybe, give or take, you know, maybe it's 3 times, maybe it's 1.5 times. You know, it's huge error bars in astronomy. Yeah, so we were able to see quite a lot tonight. So I'm really glad you came with me on this journey. So we started in our solar system with Jupiter and Saturn, and then we went to star-forming nebulae. So we saw the Swan Nebula, the Eagle Nebula. Then we went to an open star cluster. So what happens once the nebula fizzles away? And then we saw nebulae that were the sites of stellar death. So we saw a lot of planetary nebulae. We saw the Snowball Nebula. What else did we see? We saw the Cat's Eye Nebula, the Cat's Eye and the Blue Snowball, and we saw the Dumbbell Nebula. Then we left our galaxy, so those were all inside our galaxy. Then we left our galaxy and looked at M33 and M31, which are 2 spiral galaxies. One of them having no black hole, probably, and orbiting the other one, which is our big giant neighbor. Yeah. All right. Thank you so much for joining me. I'm just going to glance very briefly to see if there were any questions that were missed. Wow, lots of good questions here. Is there any evidence for wormholes? Wow. Yeah. So no, so far there is no evidence for wormholes, unfortunately. That would be fun, hey, if there were wormholes. But actually, theoretically, if you work out the math, so wormholes exist mathematically, and if you work out the math, you actually the wormholes are supposed to collapse before you even get there. So just if you work out the math. And that's why actually in Star Trek, if anybody here watches Star Trek, and they talk about wormholes, there was a big deal about stable wormholes. So in Deep Space Nine, they had like a stable wormhole, and that's a big deal. It's because theoretically they're not supposed to last. They're supposed to collapse before you get there. And those are unstable wormholes. But of course, there's basically nothing else that's scientifically accurate about Star Trek, but it's fun anyway. All right. Thank you so much for joining me here. This was really fun. It's 11:30, so thankfully nights are getting earlier and earlier, so we don't have to stay up as late to see fun objects in the sky. And hopefully we'll see you again next time, and hopefully we'll be able to see Mars. Mars is still not high enough. Unfortunately, I can show you where Mars is right now. Mars is in the east. It's right there. Mars is 7 degrees. The altitude is 7 degrees above the horizon, and that's just far too low. It has to be at least, say, 14 degrees for us to be able to see it in our telescope. Okay, so have a good night. Thank you for joining me. This was really fun. And keep looking up at the sky. Good night.